Okay, all right. Well, it's week 3 and Wednesday, and we are kind of ticking along here. So today's lecture, we'll take a look at chapters 9, 10, 11, and maybe, I don't know, but mostly today's lecture is using tidy models to kind of evaluate the performance and compare a few models, and that's going to be an important thing as you try to pick which model to use. How complicated do you want your model to be, and things like that. Okay, and so this is what we are taking a look at. And a lot of machine learning, we use empirical kind of predictive performance as our way to evaluate the model. Okay, and this is in contrast to your traditional statistics courses. So in 101A, 100C, you learn about the linear model, and you learn about the kind of mathematical assumptions that go into the model, right? And one of those things is, you're assuming that your errors are normally distributed with constant variance around whatever regression line that you have. Okay. Now, in machine learning, we kind of depart from that, and there's pros and cons to kind of the machine learning approach, which is we're in general less concerned about the actual probability model itself or the mathematical assumptions being placed on the data, and we really just care about, is it able to make predictions, and is it able to make predictions well on data that it has never seen. Okay, and that's our guideline. So we're going to say, hey, we gave you this training data and you created this model, and if that whatever system you came up with is able to make good predictions for new and novel data, then we're going to say it's a good model. And if your model gets more complicated, it's okay if it gets more complicated. It's going to fit your training data better, as long as it's still also performing well on your test data. Okay, and so chapter 9 is all about measuring performance. Now, a lot of chapter 9 in our text is about how to measure for classification methods. Okay, and today we're just going to kind of stick with regression things for now, and I think I'll cover classification on Friday. I know in the syllabus it says we'll do it in week 4, but I think I'm going to bump it up and bring up classification on Friday as well. So and then I'm sorry, on Friday I'll give you more details. I'll give you details about the project. I'm trying to clean up the data that's going to go on Kaggle and things like that. So I got a lot of work to do between now and Friday. So okay, let's just kind of go through the steps that we've done so far. Okay, so we are working with the Ames Iowa housing data set. Okay, and what we've done is we've transformed the sale price with a logarithmic function, and that's to kind of reduce the skew that we've seen. Just because when you're doing regression, we know that points that are highly skewed can greatly influence the regression as well. And so we transform sale price. We also split the data, okay, into training and testing sets. Okay, and we do that with the initial split, and I have Ames train and Ames test over here. Okay, And then we create a recipe. This is our preprocessor. This is how we are going to, rather than using a formula, we use the tidy model preprocessor things. Okay, so we do provide a formula here, but these take just the raw columns. Okay, now neighborhood is a categorical variable or a factor, and we're going to turn that into dummy variables. Okay, so there's a few steps that we do. So first we take the ground living area, and we do a log transformation on that as well. Okay, and then for the neighborhood, which is categorical, we take some of the categories that have very low representation, and we just throw them into an other category. Okay, and so that's what this step does. We take all of the nominal categories, which will be neighborhood and building type. So building type is, is it a single family home, or is it a townhouse, or things like that? And we turn them into dummy variables. Okay, zeros and ones for whichever category that they belong to. Okay, we also add a couple things. One is we add interaction terms, and the premise behind adding the interaction terms. So again, going back to kind of chapter 8, where we created these interaction terms, is that the premise is that in general the cost of a house goes up, or the price of a house goes up as the square footage goes up. But if, depending on the type of the house, so in particular, if you look at, say, a duplex or this two-family complex, even though the square footage goes up, the sale price, the value of the home, doesn't seem to increase at a greater rate. And so we wanted to kind of include this possibility that there is an interaction between the house type and the ground living area. Okay, now this is the kind of thing that you would only really discover after doing some exploratory data analysis, right? So during your exploratory data analysis phase, we don't go straight into modeling, right? When you get a data set, you create a bunch of these kind of plots to see if there's interactions and stuff between variables. You don't just start jumping in and creating a model and throwing in whatever interaction terms. I think it makes sense to do some exploratory data analysis, and so we have to pretend that we were doing some exploratory data analysis. We came across this and we decided now we want to include interaction terms in our model. And so to do that, we do interaction terms between ground living area and any of the variables. Now that we've created dummy variables, any of the variables that start with building type. Okay, because what the dummy variable will do is it does building type, building type, two-family complex, building type duplex, building type townhouse, and it's going to have those columns with ones and zeros. Okay, so that is something in in this class. We're focusing on the modeling step of data analysis, but prior to the modeling step, there's like exploratory stuff, right? Exploratory stuff. And hopefully you learn how to do exploratory stuff, and somewhere along the way, 102A, 101A, somewhere around there. Okay. And then the last thing that we do in our recipe is we want to allow for a nonlinear relationship to latitude and longitude. Okay, so again, a linear relationship would say, okay, latitude and longitude form a plane, and one corner of the city is low and the other corner is high, or something like that. Whereas what this function is doing, the NS, is saying create a natural spline, and a natural spline basically says, okay, you can just have this, rather than a straight line relationship, you can have some kind of curvature and bends into it. And we can talk about kind of some of the ideas and principles of a natural spline, but basically it just allows for some kind of flexible thing, not necessarily requiring a functional form. Okay, so we allow for that, and then the degrees of freedom. Basically, more degrees of freedom allows for a more kind of wiggly curve, and fewer degrees of freedom, is a more rigid curve, and that's what these things. So here we're creating splines with more terms. So fewer spline terms is less, is a little bit more less flexible, and as we add more terms, we get more flexibility here. And so we're just looking at how does the sale price change with latitude, and again, this is a bit of a weird idea, but we're just saying, okay, some parts of the city, certain streets are expensive. If you just imagine the city on a grid, we're saying, okay, these streets up here are expensive, these streets here are cheaper, these streets down here are expensive, or something like that. And we're kind of allowing for this this kind of relationship or something. Okay, just if you just assume the city's on something kind of a grid, right? And similarly, if you go east to west with a longitude, you would get some kind of spline thing as well. All right, and so again, this is something that during the exploratory phase, you would create a plot of one of the variables against sale price, and you say, okay, does it make sense to just treat this as a linear term, or does it make sense to kind of use a bit of curvature? Okay. Okay, and so I think I've covered these steps here, and on this slide here. All right, and so now that we've created the recipe, we bring that in and we combine it with the model and create a workflow. Okay, so again, the way the steps work is you create a recipe. Alternatively, you don't have to create a recipe. You can just create a formula. Okay, and you can use R's formula interface, and it will do some of this pre-processing things, but the recipe gives you finer tuned controls, right? Like doing the step other for the neighborhood. That's not something that's going to happen automatically with the formula. So some of these things are handy here. Okay, so what we do is we create a parsnip model. In here, we're going to create a linear regression model, and we change some of the options, and we say, okay, well, we're going to set the engine for the parsnip model to be the linear LM, just the base R tool for fitting linear models. And again, we have different options. We can use GLMNet, we can use Stan, or whatever. Okay, and we create a workflow. Okay, and we're going to call this thing the linear model workflow. And so we start off with an empty workflow. We add the model to the workflow. We add the recipe to the workflow. Okay, and we could have switched the order of these things around, because I guess technically the recipe comes first and the model next, but Tidy Models is kind of smart enough where you can just kind of say add a model, add a recipe, and even later on you can take the existing workflow and you can say remove the variables or remove the recipe or something, whatever it might be. Okay, so once we've created this workflow, then we fit the workflow to our data. So here we're going to just do the linear model workflow, and we say fit the workflow to our training data. And this is going to create our fitted model object. Okay. And so, and with our fitted model object, we can now make predictions. All right. So what we can do is we can say, all right, we can go straight to kind of the test data, and we can say, all right, let's make predictions using our fitted object, okay, this LM fit that we've created here. Now that we've fit the data, let's have it make predictions. And this is where we can start to kind of measure the performance. Okay, and so what we want to do is we can ask what are the what values do you predict? And so to do this, we're going to give it the test data, and we're going to select all of the columns except for sale price, right? So we do Ames test, and then subtract off sale price. So we just do Ames test, select everything minus the sale price, and that's just going to form our new data. Okay, so this is going to be kind of our test set. And then we say make predictions. And when you make predictions, you just get a tibble with one column. Okay, a tibble with one column. That column is dot predictions. Okay, our test data has a total of 588 rows, and that's exactly what we have here. Okay, so here I take the result of predictions and I call it Ames test results, and we want to kind of be able to measure the difference between the predictions and the actual values. So I'm going to take I'm going to bind the column from Ames test results, which is just the predictions, and I'm going to bind it to, and I'm going to here just extract out. I could have called select or pull. Just that column sale price from Ames test. Okay. Now I could have just done Ames test $ sale price as well. Okay. But this is kind of using the tidyverse expressions here. Okay. So we're going to just take test and we're going to select or pull sale price, and we just kind of bind these two. And so now we have the actual and the predicted, and we can calculate residuals. We can or the error values, and we can calculate root mean squared error. And things like that. We could do it manually. To simplify things, we can just use kind of the formulas. Now, one thing that is always kind of helpful is after you create a linear model, is you just do the predicted values versus the actual values, or actual values versus the predicted values. Okay, and that's a two-dimensional plot. And basically what you want to see is you want to see your dots very close to this line. Okay, just the diagonal line of y equals x. Okay, you want to see your the actual values and the predicted values to be very close to that line. Okay, and so in multiple linear regression, we have a bunch of variables going in here, right? We've got neighborhood and ground living area and latitude and longitude. And we're not going to create individual plots, okay? I mean, you could. In traditional, in 101A, when you do linear regression, you often create individual plots against the response variable to kind of just see, is there some kind of relationship there. Here we're going to just kind of look at the final result, the actuals versus the predicted, or predicted versus the actual. And what we're hoping is we see things line up, okay? And so here, using ggplot, I put the actual value on the x, and the predicted values on the y. Maybe you can swap them or whatnot, but here, this is what we have. We add a diagonal line, okay? AB line, the default is intercept 0, slope 1, so we don't have to change those, but you could also change what the intercept and the slope is if you wanted to. Line type 2 adds makes it dotted. Okay, we're going to add the data points here. Alpha reduces the transparency so that when dots are stacked on top of each other, they appear darker versus areas where there's only one dot. So maybe a little bit harder to see on the projection here. Okay, and then coordinate observed predicted. Kind of scales the x and the y axes uniformly here. All right, and so overall we see pretty good matching. Okay, we have a few outliers where we didn't do such a great job. So the actual sale price was pretty low, but our predicted value was quite high. Okay, and then so we have a few kind of outliers over here. And then maybe over here we have, the actual sale price was pretty high, but our predicted value was considerably lower. Okay. But overall, I would say this seems to do a pretty good fit. Okay, and so what we can do is we can take this data table that we created. So again, this is Ames test results. This is the same data frame or tibble that we're using to create this this plot. We can also just say, all right, what is the root mean squared error, right? So how different are the actuals from the predicted values, or the predicted values from the actual values? And so you can say, all right, give me the root mean squared error, okay, for Ames test results, and you name the column that has the true values, and you name the column that has the predicted values. So we're going to say truth is the sale price, estimate is the column dot predictions, and it says, okay, your root mean squared error is 0.0736. Okay. If you wanted other metrics, you can just kind of name them. All right, you call metric set. All right, and again, any of these. So we see a lot of functions here, right? And so any of these functions you're not quite sure, you just type in tidy models, and you do something like, you just give it the function that you see, and here is combine metric functions, and basically, you kind of provide the list of the different metrics that are available, right? So you got some of these listed off here, and there's different metrics that you could use. Okay, now metrics all by themselves generally not super helpful, right? It's more useful if you're able to compare metrics between different models. Okay, so these are the metrics that we get for our linear regression model. With all of our terms, we get our root mean squared error to be 0.0736, and if you just showed me that, I would have no idea. Is that good? Is that bad? We want to kind of start doing some comparisons. Okay, so as a contrast to this linear regression model, and again, this is a linear regression model that includes the variables plus the interactions plus the spline fit for the longitude and latitude. How does that compare to some other model? Okay, and so I haven't exactly taught random forest, and so that will be coming up on how random forest works. Okay, but random forest can be used for regression. Random forest can be used for classification, and so here to kind of compare our linear model against something else, we're going to create a random forest model. Okay, and so the random forest model, I follow kind of the same steps. Okay, and we're going to say, all right, go ahead and start off with a random forest. We give it the option, I want 1,000 trees in my forest. Okay. And then there's different engines that exist that are able to create random forests, and Ranger is a pretty good package, and it's good because it works quickly as far as creating random forests go. So there's there's random forest as part of. There's already a package in R called Random Forest, but Ranger actually works even faster, so we like that. So we do that, and so this creates our model. And what we're going to do is we're going to create a workflow, okay? And so to this workflow, we're not going to use the recipe, okay? We're going to just kind of provide the formula. We're going to say predict sale price based on these variables: neighborhood, greater living area, year built, building type, latitude, longitude. And the random forest will go ahead and just kind of work with these variables as they are. We don't have to do all of that pre-processing for a random forest model, because for a random forest model, when it sees a categorical variable, it starts just putting. It doesn't use dumbing variables, because the way a random forest does is it just creates divisions. Okay, so with and I'll explain more, I guess, in our random forest lecture, but it just creates divisions between sets. Whereas in a linear regression model, it needs to take the variables, multiply it by a coefficient, and it adds it to the predicted value, right? So maybe your current predicted value is 15, and then if the dummy variable is you have a categorical variable, right? And you have the dummy variable is a 1, you multiply that by the coefficient, maybe 2, and you take 2 times 1, you add it to 15, and now your prediction is 17, right? Or, for another category, maybe the dummy variable is 0, but then, for another observation, it becomes 1, and that coefficient's -3, so you do 15 minus 3, and you get 12. And so for linear models, you have to turn your categories into dummy variables. So you can kind of multiply it. You get a 0 and 1 that you can multiply by a coefficient and add to the thing. Random forest doesn't care about that. Random forest just says, oh, you know what? Red, green, and blue go over here. Yellow and purple go over here. And it just takes the categories and it divides them into kind of these splits. Okay, and so we don't need to kind of do any of that pre-processing. So here we just say, give a formula. These are the variables you're going to use. And that will be the pre-processing step that exists in our workflow. Okay, so we've got our workflow, add the formula, here's our model. And now that we have the random forest workflow, we can fit it to our training data. Okay, right. And I could have done fit RF workflow, comma, data equals Ames train, or I could use the pipe, and it provides it as the first argument. All right, is that okay? I haven't really explained what a random forest does, but is it okay that we're just kind of setting this up as an alternative model that we're going to use to start making predictions? Okay. Let me give you your first view quiz answer for today. The letter A. A as in apple. A as in apple is your first view quiz answer. Okay, so we train the random forest, and we want to say, okay, well, how does it perform? And so we're going to take our random forest, we make predictions on the test data. Okay, so here I'm going to say Ames random forest test results. Okay, we're going to make predictions, take our fitted model, make predictions on the test data, and then we take our remember, that's going to just have one column of predictions. We're going to bind that column of predictions with the actual sale price here. So kind of the same thing. We're going to take our prediction results, add the column sale price, and that's Ames random forest test results. And then we just say, all right, now calculate the root mean squared error for the true value sale price. The predictions are in the column dot predictions. And it gives me 0.0701, okay? 0.0701, and we can go back to this and we say, okay, how does it compare to the Ames test results for the linear model? And we have 0.0736, and we go, oh, okay, this one's lower. and that's pretty much it, right? So if these were like kind of your two finalist models, you could say, okay, between the random forest and the linear model, this one's a little bit lower, and so we would ultimately pick this one. Yeah, question.
Is there a reason why we take the square root of the mean square error? Is there any reason for that?
Oh, you mean why not just use mean squared error?
Yeah.
You could use mean squared error. It's just if you're talking about units, then mean squared error, you have squared units. and root mean squared error, you're back in the original units. So for example, if you're trying to like predict gains or losses for the quarter, for your company or something, mean squared error would be like squared dollars, right? We have a mean squared error of 1,500 square dollars. Okay, and what's that? I don't know. Okay, I don't know what a square dollar is. All right, it's just like a mathematical thing, right? Like in physics, I guess like square seconds kind of make sense, right? Like you talk about acceleration and it's like meters per second, so it's like meters per second squared. And you're like, okay, square second, I guess that makes sense. But then like at the same time, like what is a square second? I don't know. So anyway, so mean squared error, you get something like squared dollars. Root mean squared error, you get regular dollars. And so that's kind of the reason why we like standard deviations, where we take the square root instead of the variance. Although, so mathematically, variance is a lot more nicer and easier to work with, but then like when reporting values to non-statistics people, they would probably prefer standard deviations. Okay. So anyway, if you have kind of if these were your two finalist models, you run it on your test set, 0.0701 is lower than the other. And so you go, okay, we go with this one, right? And that's it. This is, there's like, it's a little bit scary because, we don't have a ton of tools really to say like, oh, how significant is this difference, right? I think as statisticians, we kind of say like, oh, 0.0736 versus 0.0701. Part of us is always kind of questioning like, is that a significant difference or not? And the textbook covers a way to approach that, and I'll probably do a short detour over into that, but I didn't include it into my notes. Okay, now the recommendation though is you really only want to turn to the test set at the very end. You don't want to use it as part of your modeling process. Okay. You don't want to do a model, create the test set, and run it against the test set, and then say, oh, okay, this one was the best, and then let's like refine it, because then you run the risk of overfitting your test data. Okay, you run the risk of overfitting your test data, and so what we want to do is we want to use cross-validation, or have a way to do validation within the training data before turning to the test data. Okay, and so this will kind of give you a preliminary estimate for your model performance, and you can kind of compare models during that stage. So here now we're in chapter 10, and we covered a bit of chapter 10 here. In one of our earlier lectures, when we were talking about resampling for evaluating performance, and we talked about within resampling methods, we looked at cross-validation, right? And so again, what cross-validation will do is it takes all of your observations and it breaks it up into different folds. Yeah, question.
Just to clarify, the root mean square error, and that's chapter 9, right?
Yes. So okay. Yeah, root mean squared error is in chapter 9, and that's just under the regression metrics. Okay. Chapter 9, there's a whole bunch of other stuff covering classification metrics. Okay, things beyond just accuracy. So a lot of times when we're talking about classification, you just a simple question is how many did you get correct? Okay, how many did you get correct? And that works well, especially if you have fairly even representation between your things. But then, but there's other metrics. You have kind of your ROC curve and the area under the ROC curve, and we'll get into that when we cover classification. So, but now we're going to look at cross-validation, and the idea here is, in the beginning, we split our data into the training and our testing sets. And now we don't want to touch the testing set until the very end. So with the training data that we have, we're going to kind of further split it into, your analysis set and your assessment or your validation set. Okay, so you kind of have your training and validation or analysis and assessment, and we're going to do a bunch of resamples. And kind of one of our favorite methods is this K-fold or V-fold cross-validation. So for 3-fold cross-validation, we take all of our data and we split it into 3 groups. Here we have green, yellow, and blue. And in one, we use the yellow and blues for our training or our fitting process, and we validate it against the green, and then we swap them around, and we do different permutations, and we evaluate against the yellow, we evaluate against the blue, and that would be 3-fold cross-validation. And we can do Tidy Models makes this easy for us, and it says, okay, give me your training data, all of your training data that you have, run it into this function, V-fold cross-validation. Tell me how many folds you want. And so here we're going to do 10 folds. Okay. I set an arbitrary seed. This is just the one that the textbook used so that my results would kind of match the textbook. But again, you just set an arbitrary seed because the way it splits it into these different folds is random and arbitrary. Who gets assigned to green, yellow, or blue is a random process. And so there is going to be some variation. If one person does 10-fold cross-validation and someone else does 10-fold cross-validation, there could be, slight differences between your values. Hopefully, it's not dramatic, okay? And generally it won't be. Generally it won't be, because at the end you're taking the average of 10 things, which is a lot more stable than one randomization. Okay, so this creates a fold object, okay? So we run V-fold cross-validation, and this creates a resample object, okay? Because technically there are other ways to resample your data. And we could, and again, Tidy Models knows how to fit your data or fit your model against one of these resample objects. So so back here when we said, fit your data, you just fit it against the entire training data. Now we're gonna fit it with some folds, okay? And so we're gonna fit resamples, okay? We're gonna use this object for fit resamples. Now when we do the fitting, there are some options, okay, on how the resamples get used. All right, and so as we do that, there's a couple ways we can control this, right? So if you want to adjust some of the things, so in our case, when we fit our data to our resamples, we want to save the predictions and we want to save the workflow. And these are some options here. And so again, always just it's always good to refer to the documentation. And so control aspects of the grid search, which will be control grid, and then there's also controlling aspects of the kind of fitting of the resamples. And these are a bunch of arguments, and there's stuff on like parallel processing and stuff like that. Allow parallel, and so a lot of your computers have like multiple cores, and well, I guess depending on your system. So with like the Macs, you can kind of divide up the work and do kind of work in parallel and stuff. It just happens a lot of it in the background that you don't have to worry about it too much these days, but that's what we have. Okay, so here we're gonna say, all right, save the prediction, save the workflow, and so this creates a list, and we're gonna call this keep predictions, because I think that's the thing that we're changing the default settings for. Save predictions. Oh, over here it's called save predictions today. Yeah. Okay. Save predictions. So by default, it's false, but here we want to keep them. So we're gonna pass this, and we're gonna say, hey, you know what? When we do this, we want to actually keep these predictions because we want to see how it performs. And so we have the folds, we have the resample object, we have our workflow. And so here I'm going to just take the random forest workflow, the same workflow that we created back here. Okay, back here we fit it to the entire training data, and then we tested it against the test data. But now again, the idea here is we're going to take our random forest, and we want to fit on our do vfold cross validation. Okay, so we're gonna perform vfold cross validation. So we're gonna fit on this and check performance against this. Fit on this, check performance against this. Fit on this, check performance against this. Okay, and that's done all automatically when you call fit resamples. So you don't. So now we're not going to fit on the training data. Notice we are fitting on the resampled object, Ames folds. Okay, is this all right? So there's a lot. You have to pay attention to the details in terms of like back here, you know, we take the training data and we create our resamples, okay, with the folds. And now we're going to fit to those folds, okay? And this will automatically go through the process of fitting, you know, in our case, 9 out of the 10 and check metrics against the 10th, okay? And then we're going to say, you know, we want to keep the predictions here. And so when we do the fit resamples, we're going to store all of those to our random forest results. Yeah?
Do the number of folds that based on the size of the data?
Do the number of folds depend on the size of the data? Yeah, you know, I haven't found a great answer for exactly how many folds. Folds. A lot of times it's usually some number between 5 and 10. That's... And I don't know, you know, too many folds can lead to kind of, you know, a little bit of an overfitting problem. But then too few, you know, you got this bias variance trade-off kind of thing, right? So too few, you're a little bit more. Yeah, it's subject, you know, to some issues there. Okay, but okay. So anyway, we'll go ahead and we do this. This is our random forest results after fitting our random forest to all of the different folds of our data. Okay, and so if we ask, what does the results of fitting this look like? You get this. Difficult to read result. Okay, it says resampling results, 10-fold cross-validation, and you have these things. Okay, so you have splits, you have the name ID, you have metrics, notes, predictions. Okay, so here we told it to keep the predictions, and so that's why I created this thing. And so this is each row now represents one of the different kind of folds, okay? And here we could take the splits and we could find out which elements were actually in each of these splits, okay? So these splits kind of contain the the entirety of the training data, but you can see, you know, 10% went into the assessment or validation set, and 90% went into the analysis or training set. And then the metrics are stored, okay, in these 2x4 tibbles. There's notes, and we got nothing written in the notes, right? So we see 0. There might be 3 columns. And then the predictions themselves are going to be in some big tibble here. So I can just say, all right, let's take a look at, say, what is inside this tibble here. So I'm going to say RF results. Let's look at dot metrics. And let's just look at the first entry in this thing, okay? So if I do the results.metrics and I look at the first one, these are the metrics. It records the RMSE, root mean squared error, and it also gets the R-squared value for that particular fold. So for this one, you know, if it trained it on the 90%, if it validated against that last 10%, and its estimate of the RMSE is 0.0605, and we get an R-squared value of 0.862. Okay, and then we can kind of see here, what about the second fold? And you can go through all 10 of these folds, and you'll get, you know, different values. Again, because we have, you know, a different validation set randomly selected for each of these things. So we, you know, we fit 90% and we validate against that last 10%, and so we get different values for root mean squared error, right? So 0.0605, 0.0653, 0.0752. Okay, and we want to know, okay, well, what's the average going to be, right? So we would take all 10 of these things and we want to average all of them. Okay, and that's kind of the default, right? So we can take all of these things and we can just say, there's a function called collect metrics, and it's going to go through basically all 10 of the folds, look at the tibbles, and it's going to average. It's going to average the RMSE for across all 10. It's going to average the R-squared values across all 10 of the different folds, and it gathers them together, and it says, okay, the mean RMSE is 0.0721, and the mean R-squared is 0.831. Okay, and so this is how we can perform cross-validation on our training data, right? And so how does this kind of compare? So when we did a 10-fold cross-validation on our training data, we estimated our RMSE to be 0.0721. When we actually used the test data, we get 0.0701. So that's kind of a lucky a lucky thing in that, like, we actually outperformed our cross-validation on the actual test data versus like when we estimated it via cross-validation, we got, you know, 0.072 versus 0.0701. Yeah. Question.
Is there a quick way to automate this process for different models, like different amount of predictors?
Yes. Wait. So this is, as much as I'm showing you here, this is about as streamlined as it gets. Okay, like, because if I said, hey, give me these numbers across 10-fold cross-validation, like, you'd have to write like a big for loop, and you'd have to, you know, do all of these things and stuff. So this is pretty good. This is pretty good. Okay, and this is just for the random forest model. And yes, to do multiple models, we're going to look at the workflow set, and that's the next set of slides here. Okay. Let me give you your next view quiz answer. Second view quiz answer is the letter B. B as in bear. B as in bear. Second view quiz answer. Okay. And so we get the average of these metrics across the 10 different folds, and then because we have, you know, variance between these different values, right? So these are, you know, here I got 3 out of the 10. We have variance, you know, you also get an estimate for the standard error as well. Okay. All right, is this okay? This process, what's happening, collecting the metrics and all of this. And you can also, you can look up, because we said keep the predictions, right? Under control resamples, we said save the predictions. We can actually access them. So we can take, all right, we can say, all right, let's look at dot predictions. Let's look at the first set, okay? So this first set of predictions, we're gonna get 235 observations in there, right? So we say, look at the random forest results after resampling. Let's look at predictions column, and let's look at the kind of first fold. And it says, okay, yeah, there's 235. Here are your first 10. Okay, these are the predictions we made. These are the actual sale price. You got 225 more rows. Okay. And again, you can go through all 10 of these things, but there's a function that just says, all right, collect them all. Collect all the predictions, all right? And it's going to go through all 10 folds, and it's going to add all of these up. And so in total, you're going to get your entire training set. Each observation in the training set gets one opportunity to be part of the validation set, right? So each observation in the training data gets a chance to play a role in the validation set, and so we can see the predictions made for each of these things. We gather them all up, and we can compare the predictions with the actual values here. So we collect the predictions, and we have all 2,342 cases there. Okay, and with that, you can then you can do further analysis. And so, I did not do it here. But I think they, you can create plots and stuff with okay, yeah, so here they collected all of the predictions, and they created a plot of the actual value versus the predicted value. This is the results of the cross-validation. Okay, so it looks quite similar, but over here we see even more dramatically these two observations that are extreme outliers. And so I skipped these parts in in putting these into my notes, but as you go through, read the textbook and stuff, you can see some of the things they did. And this is always a kind of a good idea. Afterwards, just take all of your data and just see how it performed. And so here we're looking at, again, remember this is the training data, where the training data is being used as a validation set, okay? So we're comparing the actual value versus the predicted. We notice these two observations, and we say, well, how can we identify these things? And, is there anything unusual? So a lot of times it's good to identify outliers, things that your model failed to predict very well, right? So, your model designed something and you say, okay, well, you know what, these observations, for whatever reason, our model is not predicting these things very well. Can we figure this out, right? And this probably requires some insight and understanding, and it is going to be a little bit harder to deal with. But here, and so the textbook says, okay, well, you know what, let's try to figure out what these two observations are. So what is one way we could identify these two observations? It's not like we can just hover over them and say it's going to tell us, right? So what we're going to do is we're going to just we're going to create a new column called the residual, and we're going to just say, okay, what's the difference between the sale price and the prediction? Okay, and then in these cases, our sale price was much lower than what we predicted, right? We predicted like 4.9, and the sale price was closer to like 4.1 or something. Okay, so we're going to create a new column there, and then with dplyr, we're going to say, okay, let's sort in order of decreasing residuals. We're going to take the absolute values of the residuals and then sort them. We're going to put them in descending order, and we're going to arrange all of our data. And so here we get our two biggest residuals, and we can see, okay, in fold 9, we predicted 4.97. So we take our results and we're going to just slice it, take the first two, and it says, okay, you got in fold 9, row 32, this was your sale price. Okay, we predicted 4.97, the actual value is 4.11. We predicted 4.93, and the actual value is 4.12. And these are the observations here. Okay, and then so how do we find these? Okay, so we're going to take so in this thing, we get the row number, row 32, row 317, and we can say, okay, go to the original training data. Let's look at that row, okay? let's look at those rows. So we're going to take the row column from the over predicted values. Okay, we're going to look at that dot row, and we're going to just kind of slice those two things. And we can get the entire row, or here they just said, let's just take a look at these columns. And yeah, for whatever reason, it's hard to tell. It's hard to tell what's going on. I don't know anything about Ames, Iowa, okay? But for whatever reason, these two homes, I mean, it doesn't seem like they would be great homes. So I don't know why our model predicted them to be so valuable. Okay, who knows, right? So, but for whatever reason, this is a 832 square foot house, 2-bedroom house with 832 square feet, which is, by modern standards, relatively small, right? I think, if you have a 2-bedroom apartment, it might be, I don't know how big do you know the square footage of your apartments that you're living in? But it's probably something around here, maybe even bigger. 2 bedrooms, probably anywhere from 800 to 1,200 square feet for a 2-bedroom apartment, something around there. Okay, so who knows? Who knows why these were performed? Did that? Okay. So that's what we get. Okay, so you can kind of look that up. All right, so what do we want to do now? Well, what we want to do ultimately is we want to be able to compare a whole bunch of models. Okay, and so what we're going to do is I'm going to back up. All right, and we'll say, okay, let's when we created our recipe for linear regression, we said, let's add these interaction terms. Let's take the latitude and longitude and add these, make spline functions out of them and stuff. And that seemed to help. But again, the question is, does our model actually improve, or am I overfitting by including these things and things like that? So what we're going to do is we're going to make 3 linear regression models. One, we're going to just take our variables. We're going to take, ground living area. We'll do dummy variables on the neighborhood and dummy variables on the building type, and that will be our basic recipe. And then we're going to say, okay, can we improve our model by including this interaction effect? Okay, can we improve our model by including the interaction effect between ground living area and the building type? And can we further, so we take a basic recipe and then we add, so we have our basic recipe like this, and then we have the interaction recipe where we take the basic recipe and add the interaction effects. And then we'll have the spline recipe where we take the interaction recipe and we add the natural splines for latitude and longitude. Okay, so we have 3 kind of like nested models, right? The basic, and on top of the basic, we add the interaction terms, and on top of the interaction terms, we add the spline terms. Okay, and we want to say, all right, how do these models perform? And I suppose I should have probably, or I could have, but I didn't, added like a 4th one where we're going to just add like some variable that, isn't really going to help us, okay? But what we're going to do is we're going to create a workflow set. So we have these 3 models, okay? And I'm going to create a list called preprocessor, okay? Or preproc, okay? And preproc is going to be a list of basically our preprocessing objects, which will either be formulas or in our case recipes, okay? And we so we're going to kind of take these 3 recipes and put them into a list. Sorry, so we provide the list made on the last slide. This is what we're going to do. Okay, so we list the different recipes that we have. We just give them names, okay, and we throw them into this this object called preproc. Okay, and then for models, I'm going to just you're going to provide a list of parsnip models. In our case, we're just going to have the linear regression model. Okay. Now, you want to kind of group these things by models that work with your recipes. Okay. So in models here, I did not add random forest. Okay. Because random forest wouldn't work well with these recipes that we've created. Okay. Because again, for random forest, we can just give it the formula and it's going to do it. And it doesn't care if it's like, if ground living area is logged or not, and it doesn't care about these kind of interaction, or it's not going to do natural spline stuff. So for that, I'm not going to, these pre-processing objects aren't compatible with the random forest. So I'm going to keep that separate, okay? And so here, to create the workflow set, I do pre-processing, and for models, linear regression, okay? And then we're going to use linear regression, and we're going to use it against these things. There's this thing for cross, and if you have, you could have like multiple different models, and then you can also do cross true. And so if you have like 3 models here and three things in your pre-processing, then it will cross all of them, and you'll have a total of 9 combinations. Right? Each pre-processing recipe with each of the models that you specify, and you can say, do it or don't. So if you say true, if you do 3 and 3, and you say true, you'll get a total of 9. And if you say false, then it's going to element-wise match the 3 and 3, and you'll have a total of 3.
But in this case, true and false doesn't matter.
In this case, it doesn't matter because I just give it one linear model thing, so it has to kind of multiply, the linear regression against all 3 pre-processing things. Okay, so this creates my workflow set, and we're going to just call this LM models. LM models is going to be my workflow set. Yeah.
How do you know like what interaction thing to do and like what spline rec to do?
Yeah. So this, how did I know? Well, okay. I didn't do any of this. I'm just following the textbook here. But how would somebody, when fitting models, do all of this? Okay, this comes from during your exploratory data analysis phase, which we're not like getting into, but it's kind of during exploratory data analysis, what do? You kind of like you group by different things, and then you create summary stats, and then you also create some plots, and you just say, all right, here's my response variable, and here's a predictor variable. Does it look like there's a relationship between this predictor and this response? Does it look like, okay, and does it look like you can create facet grids, right? I guess maybe, I don't know. Are you guys comfortable with like ggplot and stuff? Kind of? Okay, so like, do you know how to create like a faceted grid plot? Oh, okay. We need like a separate workshop. But okay, so this is a way. So you all know scatter plot, right? You do your predictor variable versus your response variable, and you can say, all right, is there some kind of relationship there? And if it looks like a linear relationship, you just throw it into your linear model as just like a term, right? But then you see, you look at it and maybe there's some curvature, and you say, okay, well, maybe I need to add like a polynomial term. Maybe I need to put in like a square, some kind of square, or some kind of transformation, some kind of non-linear term there. Maybe you see something where just a straight curve doesn't fit, and then you say, okay, well, so when you look at something like this, and you say, well, maybe there is a relationship between latitude and sale price, but a straight line or even like a single curve doesn't work, so maybe I need a spline, okay? So here is just kind of a plot where you're looking at, you could just look at one of these things, and you say, well, is there a relationship between latitude and sale price? And somebody might go, it doesn't look like it's just a cloud, right? It's not like a random cloud, like a Gaussian thing, but it looks like there's something. It's just, how do we describe this something relationship? and maybe this is where you would say I want to use a spline here, okay? And if you had a plot of like age versus height or something, you're trying to predict height, and you use age. Well, age is going to be helpful, but then again, you wouldn't just use a straight line. You'd have to probably fit some kind of spline that says, okay, people grow, and then they stop growing at some point, okay? And so this is where you do something like this, okay? How do we know about the interaction terms, okay? The interaction terms, you can kind of discover these when you create faceted grids, okay? So a facet plot allows you to look at, basically it's a scatter plot between gross living area, I've been calling it ground living area, but gross living area and sale price, okay? Gross living area and sale price, but we're separating it based on different categories, okay? And so here we have 5 different categories. And so to do this, okay, so this part you understand, right? ggplot, map the gross living area to X, aesthetic the sale price to Y, okay? And so this is, here we're looking at, we're unlogging, we're exponentiating sale price, okay? And then we do geom point, okay? So that would just create a scatter plot. Here, facet wrap says take this categorical variable, building type, and create 5 different scatter plots, 1 for each of the building types, okay? And this effectively will just create the scatter plots, okay? The geom smooth will add like a trend line for each of these things, and that helps kind of detect, oh, is my slope changing rapidly for any of these things? And then you can add, these are just like, do I add scales or anything like this, okay? And so here, scale X and scale Y is handy for us because we're dealing with things in log scale. So, okay. But this facet wrap will take, and it doesn't have to be a scatter plot. It could be basically any kind of plot. You have to give it a categorical variable though, and it will create the same plot. So you can do a histogram mixed with a facet wrap, and it will create a histogram of sale price for this category, a histogram of sale price for this category. So whatever it is, you just add facet wrap tilde some categorical variable, and it will create several of these things. So during the exploratory data analysis phase, you might have created a graph like this that gives you an indication that, oh, you know what? There might be something here that I want to include into my model. So how do we know? The answer is from exploration and guessing. And a lot of these things is you're exploring and you say, well, maybe there's something there. You throw it into your model, and then the performance goes down. Okay, and then you go, oh, maybe I'm overfitting. Okay. Okay, so here's our models. Okay, so when we ask what does our linear models object looks like, okay, we get this tibble, okay, and it says it's a workflow set. Okay, we have 3 rows, one for the basic, the interaction, and then the splines, and then we look at these things. All of these, the option and the results currently are empty. If we go to info, we can say, all right, well, let's look at what this tibble has. Okay, so we look at basic LM. What's inside this tibble? Okay, so we're going to look at LM models $info, and we'll look at the first entry there. And it says, oh, what it is a workflow. The pre-processing is a recipe, and the model is linear regression. Is there any comments? Nope. Okay, and then what's in this workflow? We say, okay, linear models $info1. What's in the workflow? And it says, okay, here's your workflow. You've got a linear regression model. Your preprocessor is this recipe. Whoops. What did I do? Okay, here's your recipe. This is your recipe. Your recipe includes a log step, making an other category step, a dummy variable step. This is your model. And so, we saw this when we were talking about workflows, and this is what we have. Okay, so it contains all of the information about each of these things in here, and we can explore any of these things, and we'd see, okay, the recipes change for each of these things. Okay. All right, so what do we do? Now that we have workflows, we're going to use this function workflow map. Okay, and this allows us to run the same function over all of the workflows inside a workflow set. Okay, so the function that we want to do is we want to run fit resamples. Okay, so fit resamples, again, if I go back a bunch of steps, fit resamples is how we fit a workflow to our vfold resampled data, right? So we take our Ames folds is what we did with vfold cross-validation. This is our 10-fold cross-validation, and we said, okay, take this random forest and run fit resamples on it. It gives us this results, and we say, okay, we got the results from the 10 different times we ran it on the 10 different folds, okay? And then, we wanted to just kind of take the average of the root mean squared error across all of those 10 different folds, okay? So we want to do the same process of getting this thing, but now we have 3 different models to do, okay? 3 different models. And so we're going to run workflow map, and we're going to take workflow map, and we're going to say run fit resamples across the 3 different workflows. So we have these 3 different workflows. We want to do fit resamples on the basic LM, fit resamples on the interaction linear model, and fit resamples on the splines LM. Okay, and that's what workflow map is going to do. Okay, so for workflow map, we take our linear models and we're going to pipe it into workflow map, and we give it the function name fit resamples. This is the function that we want to run over and over. So we do that. Okay. And there are a few options that we need to give it, okay? So one is when you do the workflow map, there's a couple options. You can set a seed, and you could set verbose to be true, and it will kind of tell you what it's doing as it's doing, okay? And then as far as fit resamples go, okay, when we ran fit resamples here, we needed to give it these 2 options, right? Or arguments. We need to say, okay, when you do the fit resamples, fit it to this data, okay, the resampled data here, Ames folds. So we have to provide that, and then we also want to keep the predictions. So we do that over here, okay? And so this is all on the same kind of line. So after it does verbose true, you kind of provided just more arguments, and we can say, okay, for the fit resamples run on Ames folds, and as far as the control run we want to keep the predictions, okay? And it does that, okay? And so it says, okay, we're going to look at the resampling, and it does it for basic LM, it does it for interaction LM, it does it for splines LM. And now it is done, okay? So it stores it. We told it after you do this, store it back into LM models, okay? So what's the difference between here and here? So notice options and results now have stuff in there, whereas back when we first created the LM models, when we just specified it, okay? So when we created the workflow set, we only had stuff in info, options was empty, results was empty. And they all say 0 and 0, meaning there's nothing there. After we ran workflow map with fit resamples, we ran fit resamples on everything in the workflow. Now these things are filled out, okay? And so I can say, okay, well, what's in the option? Okay, so for basic LM, what were the options? It just says, oh, these are just the 2 things that you gave it, right? We said, okay, fit it on Ames folds and give it, and fit it on keep prediction, and it says, okay, here we have, those are the things that are contained in here. So really the stuff of interest is going to be LM models $results, okay? And so if you take a look at the results here, what does this look like? This is the result of running fit resamples, okay? So we ran fit resamples, and we have one for each of these models. So again, comparing it, going back, this is what the fit resamples looks like. The results of fit resamples looked like for the random forest, and that's exactly what we have here, okay? This is the resampling results when we did fit resamples to the first model, basic LM, okay? So I think this is what you're asking. You're saying, how do we efficiently do this across a bunch of models? And this is exactly what we're doing. We map that function fit resamples across our workflow, and it does it, or across our workflow set, and it does it for each of the different workflows that we specified. Okay, so I have the fit resamples, the results for this one, and the results in this one, and the results here. Okay, so it's kind of like tables are nested inside other tables. Okay, but notice everything is still tidy in that, like, everything is, you know, a row and a column, and it's just within the column, within here, you have like a nested table that you like expand out, right? So we have the fit resamples object, and again, we can take any of these things. I can pull out the metrics for this particular fold, and I can, you know, average them all, or I can just say, you know, what is the thing I want to do? Well, what I want to do is I want to collect the metrics, right? I want to collect the metrics here, and with this, we can just say collect the metrics on this object directly, and it's going to collect the metrics for this one. It's going to collect the metrics for this resampling result. It's going to collect the metrics for this resampling result, and it's going to report them all. Okay, so I say collect the metrics, and it does it across the 3 different workflows that we provided, and we can see, okay, the root mean squared error for the basic is 0.0803. When we added the interaction term, it goes down to 0.0799, and we added the splines, it went down even further to 0.0785. Okay, and this is actually good, right? Like, the fact that it's going down is actually good, and we can kind of be confident, a little bit more confident in this, because we are using cross-validation. Remember, these numbers are done by, you know, splitting our data into training and validation, or analysis and assessment sets, you know, training and validation sets, and we're always validating against data that the model hasn't seen. Okay, so we don't have to worry about like overfitting this particular thing because we're using cross-validation here. Okay, whereas if you just kept running against the training data and measuring your metrics against the training data, then you greatly run the risk of overfitting. There's always a risk of overfitting a little bit, but we can feel pretty good about these things. Okay, R squared values, what we see is it goes up from 0.791 to 0.793 to 0.800. Okay, again, they're going up, but you know, only kind of slightly. We can measure the standard errors here as well. There is a nice function called autoplot. All right, autoplot will automatically do these things. Now what we want to do here, before I get to autoplot, I want to actually combine these resample results with the random forest one, because I want to compare these 3 models along with random forest. Okay, so I can take the random forest results. Remember, the random forest results looks just like this, right? Except it was fit using the random forest, right? If you look at the resampling results. Okay, so we can take that resampling results object and we can turn it. There's a function that says as workflow set. Okay, so this is the random forest resampling object that looks a lot like this, just with the random forest results, and we're going to turn it into a workflow set, and that kind of converts it into a row that looks like one of these rows. Okay, so I can just take this row and I'm going to just add this row to the other 3 rows. Okay, and that's what I have. So with 4 models, I'm going to take the random forest results turn it into a workflow, and I'm just going to add that. I'm going to do bind rows and add it to the 3 other workflows in our workflow set. So now I have a workflow set with 4 different workflows. Okay, is that all right? And so even though, and again, I did not want to just add the random forest into our original workflow set, because with our original workflow set, we had like 3 different recipes, and we said run it with linear models, linear regression, and those recipes weren't compatible with a random forest. So when we specified the random forest, we just gave it a formula for the pre-processing. So you kind of have to separate out your workflows with these workflow sets based on kind of compatible recipes for pre-processing, and then but then you can kind of join them all back together. And so now I have 4 workflows in my workflow set. Okay, is that all right? Does that kind of make sense? All right, and then now that I have all 4 workflows put together here, I can say, all right, let's run autoplot. Okay, so automatic plot can be used for different things, and so here it plots the metrics. Okay, so here we have root mean squared error, and we see, okay, it's lowest for the random forest, and you know, for the 4 different models, it's the we have the basic one, 1, 2, 3, 4, okay, and then R squared. Wait, did something? Basic root mean squared error 0.08. Okay, now I'm a tiny bit confused about the order of these things, but we have these. The auto plot will add this, okay, and so we have the R squared being plotted, and we see R squared is highest for the random forest, and root mean squared error is the lowest for the random forest here. Okay, the textbook actually creates a better plot. I probably should have copied that, but in the textbook they added labels. Okay, and so to add labels, there's a function or there's a library called ggRepel, which is I don't know if you ever used, but normally you can add text, and you would use ggtext or geomtext, okay? And text repel, so geomtext will just place the text on the thing, but sometimes it puts it right on top of the dots, and or like the text lands on top of each other, and they get in their way, and it becomes impossible to read. And so text repel is like aware of where it's located and where other text is located, and so it tries to place text someplace smart. Okay, so here I just call auto plot, and then we're going to say add text repel, where the label is the workflow ID, and then it adds the text, and it kind of adds a little kind of label here to kind of say these are the different workflows that it's producing. I want to kind of just maybe so that's it for the slides that I've produced, but I want to just fast forward a tiny bit, just because I don't know when I'll have time to get into this, because we spent a lot of time on tidy models, because I wanted to give you these tools so you can start on Friday when I give you your project. You can start kind of working on these things, and you can just kind of fiddle around, even if you don't fully understand how the some of these different models work. You can start fiddling around with them, okay? And then so, you know, with the other class, I want to start explaining like what's happening with these models, and maybe not get into like the deep algorithms of how these different models, like how does a random forest work, but just kind of give you these conceptual ideas of what a random forest is doing, okay? Because right now I just said, you know, here's a random forest, and we're treating it like a black box, and I just, you know, I want to get into, you know, some of these things, you know, classification models and stuff like that. But so I'm going to just kind of fast forward to chapter 15. where we are going to, so here we kind of, we had like three linear regression models plus the random forest model, and we kind of compared those 4 models together. Here we can just say, well, what if I wanted to screen a whole bunch of these things? Now, you're going to see references to some of these other chapters: model tuning, grid search, and iterative search, and you should probably take some time to skim over those chapters. But so this is kind of like maybe a bit of a shotgun approach. We're going to just throw all the models we have at a data set, okay? And so this data set, we're going to look at some concrete data, okay? So I guess if you're like materials engineering, you're like trying to figure out how to design some concrete, right? And so you can mix different kinds of stuff, and I don't even know what these numbers mean, but you can have like so much cement and the blast furnace slag and how much fly ash, I don't even know what that is. How much water do you mix in? How much super plasticizer, coarse aggregate and fine aggregate, and age and stuff. And like these are the different things, and this is, I guess it's like mixing a cocktail, except it's like the goal is concrete and you want concrete that's strong, okay? And so we're going to measure the compressive strength of concrete. So it's like how much strength can it endure after it cures. So anyway, this is the data set that we're working with. We want to try to be able to predict compressive strength. And there's something a little bit strange about this data, in that some of these settings, okay, so this combination of 540 cement and 0 for this and 0 and 162, some of these things, they ran like the same settings multiple times, and they recorded like different compressive strengths, but they didn't do that for all of them. So some of these things, you have kind of these duplicate rows where all the settings are the same, but maybe the compressive strength was recorded just slightly differently. So to kind of address that, you're going to group by, you're going to find groups where the entire row is duplicated, and then you're going to just kind of take the mean of the compressive strength. That's what this row does, okay? And so it reduces, it eliminates maybe like 38 rows from the data set. Okay. Okay. So we split it into training and test. We create our cross-validation folds. Okay. And then we create a couple recipes. Okay. One is, what if we normalize all the predictors? So that's like turning, standardizing them so they all kind of have the same standard deviation. And then some of the predictors, okay, we turn into, we add kind of a polynomial thing, and we have interaction effects between all of the terms, okay? So we're going to add, polynomial things, and we're going to add interaction effects between all of the different terms. So there's 8 different terms, so that's 64 different interaction effects. Or is it, no, 8 choose 2. So not 64. 8 choose 2 is something else. 56 divided by, I don't know.
It's factorial over.
Yeah, something.
Minus
I think it's 8 times 7, or 28 interaction terms. I think 8 choose 2 is 28, I think. Okay.
8 times 7 over 2.
Yeah, 8 times 7 over 2, yeah, 28. Okay. So okay, so you'll have 28 interaction terms if you do this. All predictors. Okay. All right. And so these are all of the different models that we're going to just kind of throw at it. Okay. And okay, so linear regression, fine. Okay. Neural net. So that's going to be a single layer neural net. MLP. Mars, I don't even know what that is. Okay. Support vector machine with a radial basis function. Support vector machine with a polynomial. K-nearest neighbor, which can also be used for regression. We often think of it for classification, but K-nearest neighbors can be used for regression. decision trees, okay, cart, bagged trees, random forest, boosted trees, cubist. I don't know what cubist is. Okay, and so we got all of these different models, and again, you can, I think I showed you, you could open up the little thing and click the buttons, and it will kind of produce a lot of these specifications, and maybe you have to set a few of these things, but I think overall, the reading, now that we've kind of can read tidy models, I hope maybe you can see that specifying these different models is not overwhelming to do, and it didn't require us to like learn the ins and outs of all of these different packages. Okay, so we say, okay, we want a nearest neighbors with some of these different arguments. Okay, and so tune, you see this tune function, which is go back to chapter 12 to kind of read a little bit about that. Okay, and then we're going to create a workflow set. Okay. And again, we have to create separate workflow sets based on the combinations, the preprocessors, recipes that are compatible with the list of models. So I'm going to combine this recipe, the normalized recipe, which is compatible with these 4 models. So we're going to create a workflow set there. And then, and we can extract maybe this, okay. And then here's another workflow set. Okay, this workflow set is going to be the preprocessor here is just going to be a list of workflow variables. Okay, predictors, it will be everything, and the outcome is just compressive strength. Okay, so this preprocessor has no recipes, just a list of variables, and that's going to work better for basically all of the tree-based models. Okay, so cart is tree-based, cart bagged trees, random forest is tree-based, boosting is tree-based, and I don't know what cubist and Mars is, but maybe they're also tree-based, I'm not quite sure. Okay, so this is another workflow set, okay, because again, we're trying to match the pre-processing recipe, or in this case, it's not really a recipe, it's just a list of variables with the models that are compatible with that. Okay, so we do that, and then finally, the linear regression, we create one more workflow set where we have the poly recipe with linear regression and I guess k-nearest neighbors will work with the poly recipe, and we group those. Okay, and so I have a few different workflow sets. I got the normalized workflow set, which combines one set of recipes with models. The no pre-processing workflow set, and then the with features workflow set. Okay, and then all of those workflow sets we bind together. So I just do all workflows. I'm going to bind the no pre-processing workflow set with the normalized workflow set with the with features workflow set. So I'm going to kind of do all of those together, and I get all of my workflows here. Okay. And here, just to kind of make the workflow IDs easier to read, they did a little bit of, they said anytime you see the word simple or normalized, just get rid of it, okay? Because the standard naming convention is it takes the recipe name, in our case, the simple, the recipe name, and it kind of prepends it to the things, but that's going to be a little bit annoying. So all we did was we just said, okay, fix the thing to get rid of some of those names. So now we have just all 12 of the different models right here in all workflows. Okay, and then there's a few options here where you can kind of control, and we can say save the predictions and save the workflows and try to parallelize everything, and then you run the results. Okay, and then so you do. We're going to take all of the workflows, and we're going to run it against the workflow map. Okay, and it's going to try to fit this. And if you were to run this thing, it takes a long time. Okay, it takes a long time. So here it reports back. So some of these are faster. 12 seconds for Mars, 2 minutes for cart, 1 minute for the bagged carts. Okay, but boosting takes around 12 minutes. Cubist around 10 minutes. The SVM was 37 minutes. Jeez. Okay, so I'm not gonna run this. Okay, but you can kind of set it, come back after lunch, and see if you got your results. Okay, and you can see it goes through each of these 12 different workflows, and it tries to run a whole bunch of these things. Okay, and then you can kind of take a look at the results, and you can say, okay, well let's pull the metrics out, and you can look at this, and at the end you can say, okay, let's auto plot all of these results across all of these things, and you can see, okay, the boosting and the Q, these ones kind of had the best performance, whereas K nearest neighbors didn't, kind of the worst performance here. And so this is kind of, and you can, now that you can start kind of maybe refining some of your better performing models to see if you get something even better or stronger there. So that's, again, kind of skipping ahead. I want to, so I'm going to leave you with just kind of this textbook as kind of a guide to help get you through, for the, your project and stuff, and read the chapters that I did not cover, and we'll spend a lot of the other time in class going over some of these different models and how they work. Yeah, question.
So how useful is that tuning function? Does it just automatically tune and pick the best one?
Yeah, it gives you yeah, it's good. And helping you kind of figure out some of these the settings to use for some of these things, and there's default things, and again, you can kind of bump them up or down as needed. Let me go ahead and give you your last view quiz answer, which is the letter B. B is your last view quiz answer. And that will be it. Okay. Have a good rest of your day. Oh, Friday, I'm gonna have to teach remotely. Okay. On Friday, I'm gonna teach remotely, so don't come to class. I'll do it remotely, and I'll record it and post it. So Friday will be done remotely. Okay. We'll see you guys later.